Inside every single jet engine, there's a battle raging. It's this invisible, super high-speed storm of air. And engineers are locked in this scientific showdown, using these incredibly powerful digital tools to try and see what is really going on. Okay, let's dive right into this battle between pixels and physics. So this is the prize fighter. I know it looks simple, but this little piece of metal is right at the core of our modern world. And if you can make it even a tiny bit more efficient, you can save millions in fuel and emissions. The problem? The air flowing around it is violent, it's chaotic, and it's almost impossible to predict. So right there, that's the central challenge for engineers. I mean, you can't just guess, right? You need a way to actually see this storm to understand its every twist and turn way before you ever go to build a single thing. And that is where computer simulation becomes just absolutely essential. So in this explainer, we're going to break down this whole scientific contest. First up, we'll look at why we even need to simulate this invisible storm. Then we'll meet the 3 digital cameras that are competing to capture it. We'll see the real-world test they were judged against. We'll compare their results head-to-head. And finally, we're going to ask about the high cost of getting a perfect picture. Okay, so why go to all this trouble? Well, it's because understanding the fundamental physics of how air moves is the key to designing everything from more efficient jets to cleaner power plants. If you get it right, you save energy and you push technology forward. It's a huge deal. The main tool for this job is called computational fluid dynamics, or CFD. And the easiest way to think about it is like a virtual wind tunnel that lives inside a supercomputer. It uses all these complex equations to create a digital version of that invisible storm, letting us see how it's going to behave without ever building a single physical part. But here's the thing, not all CFD is created equal. In this study, researchers decided to pit 3 different methods against each other to see which one could best capture what's happening in reality. So let's meet our contenders. All right, this slide is where we really start to see the differences. The best way to understand these methods is to think of them as different types of cameras. So first, you've got URANS. It's like taking a long exposure photo of traffic at night. You see the general flow of headlights, but all the individual cars are just blurs. It's fast, but you lose all those critical details. Then there's URANS, which is a step up. It's kind of like a time-lapse. You start to see the bigger patterns, the major movements, but the quick, chaotic gusts of wind, they're still missing. And then you have LES. Now this is our high-speed, slow-motion camera. It's designed to capture the big, powerful swirls of the storm in perfect detail while making really smart estimates for the tiny, less critical bits. And this visual just illustrates the difference perfectly. On the left, with URANS, the computer has to model, which is basically a fancy word for guess, the behavior of all the turbulence. But on the right, with LES, the computer calculates the big, energy-filled swirls directly. It only has to model the tiny, much more predictable bits. It's the difference between trying to sketch a car from memory versus tracing a photograph of it. Okay, so we've got our 3 digital cameras. But a simulation is totally worthless if it doesn't match the real world. So the researchers needed a benchmark, a real-life photograph of that invisible storm to judge these simulations against. To do this, they used a wind tunnel and some seriously high-speed imaging to capture what was really happening to the air around the blade. And they were looking for 4 very specific, very complex events. You've got these vortices shedding off the back, you have pressure waves shooting upstream, you have those waves interacting with the next blade in line, and then you have these tiny vortices forming right on the blade's skin. The challenge was simple. Could any of the simulations see all 4? All right, the stage is set. The real-world data is in. It's time to put these digital contenders to the test and see who comes closest to capturing reality. First up is URANS, our long exposure camera, and you can see it immediately. It's just not capturing the action. The simulation on the left is smooth, kind of blurry, and totally stable. The reality on the right, it's dynamic and chaotic. URANS completely, utterly misses the storm. So let's move on to our time-lapse camera, URANS. Now this is much better. It actually sees the vortices shedding and some of those pressure waves. But look closely. The structures are smeared, they look washed out, and they die out way too quickly compared to the real thing. It gets the general idea, but not the crisp, crucial details. And now for the main event, LES, our high-speed camera. And wow, the result is just stunning. The simulation on the left is basically a dead ringer for the experiment on the right. It captures the sharp pressure waves, the tight little vortices, how they interact. It's just an incredibly detailed and accurate picture of reality. And don't just take my word for it. The researchers themselves were crystal clear. In their own words, only LES offered a complete view of the complex physics, identifying almost all the phenomena they saw in the real-world experiment. Visually, we have a clear winner. But in engineering, pretty pictures are not enough. You need the hard data to back it up. And this graph, this is the proof. It shows the pressure on the blade's surface. The little squares are the real experimental measurements. The solid black line, that's the LES prediction. And just look at how perfectly it traces reality. Now look at the diamonds for URANS. They're way off. They're even predicting a shockwave that doesn't even exist. So the crucial point here is that LES isn't just prettier. It's quantifiably, undeniably more accurate. Let's look at one more data point. How well did the models predict the timing of the turbulence? Well, URANS was off by 26%. That's a huge error. LES, on the other hand, was off by only 4%. So it's not just getting the shapes right, it's getting the actual rhythm of the storm right too. So the case is closed, right? LES wins, everybody should just use LES from now on. Well, here's the twist. This incredible accuracy, this perfect picture, it comes at a staggering price. To get that high-speed, slow-motion shot, LES required over 100 times more computing power than that simple, blurry URANS simulation. 100 times. That is just a massive, massive leap in resources. Here are the raw numbers from the study. The simple URANS simulation took 5 CPU hours. You could probably get an answer in a workday. The URANS model, 56 hours. So you're waiting more than 2 full days. And the incredibly accurate LES, 534 CPU hours. In the real world, that's the difference between getting an answer this afternoon versus getting one maybe 3 weeks from now. And that leaves us with the ultimate engineering question, doesn't it? In a world that's driven by deadlines and budgets, this is the trade-off that engineers face every single day. Do you need a fast, blurry answer right now? Or do you need a perfect, crystal clear answer a month from now? As computers get faster, that gap is going to shrink, for sure. But for now, that choice between speed and perfection, that is the real showdown.